Good evening, everyone, and welcome to another virtual Science on Tap. I'm Linda Deck, the director of the Bradbury Science Museum here at Los Alamos National Laboratory. You have come to learn virtually from the scientists themselves. That's what Science on Tap's all about. The latest cool research being done here at Los Alamos National Laboratory, and we've got a really cool scientist with us today. Today's topic, deep sea data diving with Dr. Charlotte Rowe. Science on Tap is a program of the Bradbury Science Museum here in Los Alamos, New Mexico, with support from the Los Alamos Creative District. Many thanks to Lauren McDaniel, the Los Alamos Main Street Director, and the Los Alamos Creative District Curator, Jeremy Smith. Here's Jeremy right now to tell us more about upcoming Creative District events. Jeremy?
Thanks, Linda, and big thank you to Bradbury Science Museum for hosting and organizing the Science on Tap this evening. I also partner with the Historical Society to bring the History on Tap and the Peak at the Nature Center to bring Nature on Tap. That's coming up next Monday, May 24th, also at 5:30. We have a panel to discuss recreation renaissance. So it's a group of outdoor recreation business owners. They're going to talk about how they got started, obstacles they've encountered, and some of the success stories. As always, with the On Tap series, we'll be followed by live question and answer. So if you're interested in that one, go to either the Nature Center website at Peak or the Creative District website, losalamos.creativedistrict.com, and you can register for those events there. They are free, but they are virtual, so you need to register so you can attend. Also, this summer, the Creative District will be again hosting the Tuesday at the Pond entertainment series. So that will be every Tuesday from June 1st to August 3rd at the Ashley Pond stage. And yes, we will be live. Yes, it will be in person. Yes, it will be limited to 150 people for the COVID restrictions. As those are in place, we will have digital tickets available, all that information to come. And also, if you want to see the musical lineup that we have, check out the Creative District website, creativelosalamos.com. And Linda, thank you once again. Looking forward to this evening's presentation.
Jeremy, thanks so very much. I appreciate it. And here are some more upcoming programs that you won't want to miss. Next week, on Wednesday, May 26th, we will host Frontiers in Science, Protecting the Power Grid with Physics, featuring Raymond Newell. He will give us an exciting look at how encryption through single particles of light can keep our energy grid secure now and in the future. Frontiers in Science is a presentation of the Los Alamos National Laboratory Fellows. Then, on June 10th, our friends with the Bradbury Science Museum Association, our affiliated nonprofit, will present the online program Night with a Nerd, Exploring Mars with Perseverance and Ingenuity. The special guest will be Dr. Roger Wiens. He will talk about the latest details in the Perseverance rover's exploration of the red planet. So here's how Science on Tap works. You have joined us tonight. That's brilliant because we rely on you to be there for this program to work. Our presenter will give about a 30-minute backgrounder on a scintillating research topic going on here at the laboratory. And then it's up to you to ask questions and keep the conversation going. So it's all according to what you'd like to learn about, according to what our speaker has presented. Please feel free to bounce a question back to the question queue from what you've heard from another questioner so that we can kind of have a great conversation, even virtually. So write your questions into the Q&A, not into the chat. Make sure when you write into the Q&A, you send it to the panelists. That way I can see them and I can serve them up to our speaker. Also, for having a great experience, you're going to want to put your screen in full screen mode if you haven't done that already. So that will make your very best WebEx experience. So I hope we can have a wonderful conversation. So our presenter today, as I mentioned, is geophysicist Dr. Charlotte Rowe. She's got a very interesting past. She grew up an Air Force brat, moved around a lot, had 12 different schools by the time she finished high school. That might be some kind of a record. That's pretty awesome. She started college actually as a music major, but in Arizona, but she switched to geology, then transferred to New Mexico Tech to finish her bachelor's degree there. She worked as a geophysicist for a few years in oil exploration, and then she went on to Alaska to study volcanoes and earned her master's in geophysics at the University of Alaska Fairbanks. I love this. Her thesis volcano was in Antarctica, so she spent 2 field seasons down there. So I had a field locality. I'm a paleontologist. She had a thesis volcano. I love that. I love that. She stayed in Fairbanks for 14 years, working at the Alaska Volcano Observatory and Earthquake Center. She came back to New Mexico to finish her PhD in geophysics at New Mexico Tech, focusing on volcanoes. She did a postdoc after that took her to Wisconsin, Switzerland, and Italy, and then came to Los Alamos in 2002, and she has been here since then. So a very nice long career here at the lab. Her work here is primarily centered on detecting and characterizing seismic events based on what their waveforms look like. But she also does Earth modeling using seismic data, gravity, and in one fun project that she did, she imaged the shallow geology of Los Alamos Canyon using cosmic ray muons. Very interesting stuff. Among her many distinctions in her expansive career, here's just a couple of them: served as Alaska's deputy state seismologist, taught at both University of New Mexico and New Mexico Tech, and she has been a recipient of the Hammer Award from the National Performance Review of the Office of the Vice President of America under Vice President Al Gore. This is my favorite. The U.S. Commission on Geographic Place Names designated Rowe Nunatax. I pronounced that right, yes?
You did.
Rowe Nunatax in recognition of her contributions to Antarctic geoscience. Now, a nunatack is an isolated peak of rock projecting above a surface of inland ice or snow. So that's pretty cool.
I have my own rock.
You do. You have your own named rock. Char also serves on the International Joint Task Force for Smart Cables and the Global Seismographic Network Steering Committee, and has served on the National Research Council. So welcome, Dr. Charlotte Rowe.
Thank you. I'm so happy to be here.
Glad to have you.
Shall I get started?
Please.
Okay.
We look forward to it.
So I'm going to talk about the Smart Cables project from the perspective of a seismologist, because that's what I know. The smart cables are intended to do some other things too. But it's a project that is just getting underway. There's still a lot of kinks to work out, not in the cables, but in the plan for the project. And it's a very exciting new frontier in seismology, as well as climate science and oceanography. And I know a lot of people aren't aware of the project, so I thought I would bring you up to speed. But first, before I do that, we have to have a little bit of context. So I want to talk a little bit about the Earth, because as a geophysicist, I'm going to be talking about the Earth. You can see the dinosaurs in the upper left-hand corner here are looking at a very simplified model of the Earth. And this is the one we're all familiar with the crust and the mantle and the outer core and the inner core. It's a pretty good model on average for characteristics of the globe, but in fact, in any particular place, it's not very good at all because it's just an average over the whole globe. So if you look down beneath the dinosaurs, you'll see a cartoon that shows a lot of stuff that's going on geodynamically under the Earth. And you can see we have lithospheric plates from the ocean diving underneath continental plates, and that's producing volcanism. The two plates squishing together are squeezing up a mountain range as well. And then we have deep molten rock coming up through the mantle, coming up to the surface under the ocean and spreading the ocean plates apart from one another. And so you get submarine volcanoes and you get all these faults and fractures as a result of all the stresses on the rocks. So this is pretty complicated. We can get even more complicated if we look up in the upper right-hand corner, and you can see this is just a photograph taken from a vantage point of very shallow crustal rocks in some mountain range. I'm not even quite sure where this is, but you can see they've been bent and folded and broken and pushed over top of one another. So the finer scale you get at the Earth, the more complex it seems to be. We can actually characterize this from a seismologist's perspective and come up with complicated 3D models of the Earth using a technique that's called tomography. And down here below the rocks, I show you a slice through a tomographic model that was produced of the Earth that shows how we're able to actually capture three-dimensional features of the globe using this method called tomography. Well, what is tomography? Tomography was actually developed in the medical field, and it's a technique where you can send energy through an object at all different angles, recorded at receivers in all different locations, and use the impact of that object on the energy in order to back out a three-dimensional model of the object. So here we've got a sketch of a person strapped to a table in good Frankenstein form, and there's an X-ray source and there's several X-ray receivers underneath her. And in this case, the source and the receivers will rotate around her in a circle, and you get all these crossing rays, and you can actually build a model of her insides using a grid, a model grid. And then here we have examples of slices as you move through her of what her body looks like in 3D. And this technique is the computerized tomographic or CT scanning, otherwise referred to as the CAT scan. Well, we can do that to the Earth as well. And we have a lot of seismic stations, seismometers, located around the planet. And in this upper map, the pink dots are the locations where every seismometer that we know about that has ever recorded seismic data has existed on the planet. And the blue dots show all of the hundreds of thousands of earthquakes in the earthquake database that our group at Los Alamos has. And of course, if you have lots of sources and lots of receivers, just like the Frankenstein image of the lady, you can shoot rays through the body, in this case it would be the Earth, and you can build an image of what's going on inside the Earth. But, as you'll notice on this upper map, there's a lot of places where there aren't any earthquakes and there aren't any seismometers. And one of the biggest gaping holes is under the oceans. Most of the earthquakes occur at the plate boundaries, or the ring of fire here, and there's some other plate boundaries around here. You can see the earthquakes. And most of the seismometers are, of course, located on land because it's easy to get to. That's where we've been able to put them. However, that's just like having blinders on. If you look at the lower map, this is a map of a tomographic model that Sandia and Los Alamos generated a few years ago. And what you're seeing here in the colors, the blue colors and the orange colors show you where we've been able to characterize the seismic speed of the rocks. Faster rocks are orange to yellow, slower rocks go down into blue. And this is compared to a very simple starting model like the one those dinosaurs were looking at, where we've been able to change the model because we have data. all of the black places on here, the model stays the same as the original simple model, not because it was right, but because we have no data.
So Shar, I mean, so those earthquakes act like that emitter, and they propagate through the earth when they occur. And if only you had a seismometer everywhere, you'd be able to see everything about the earth. But we
Yes.
just don't have them in so many places that we'd love to have them.
That's right. Exactly. Yet you put your finger right on the problem. So, what can we do? Well, to the rescue are things we call ocean bottom seismographs, or OBSs. That's the first step in helping to improve this picture. And there is a program run by the National Science Foundation called OBSIP, or Ocean Bottom Seismic Instrumentation Pool, where researchers can propose to borrow some of these instruments. And if they get funding for the experiment, they can go out, and you see in the upper right-hand corner, here's an OBS, or ocean bottom seismograph, getting ready to be deployed in the middle of the ocean off of a ship. And the map on the left shows the locations where so far there have been OBSIP experiments deployed and seismic data have been recorded. Now, the problem with this kind of experiment is, first of all, it only lasts a year or two at most. So you can't use it for regular monitoring of earthquakes because the instrument's not going to be there for very long. Second of all, it's extremely expensive to put these instruments out and then retrieve them. Because communicating under the water is so difficult, they store all their data on board, and you don't get the data until 2 years later when you go out and you haul that instrument back on your ship and you can download it. So there are limitations for our purposes of just how useful these could be. Although if there's an OBSIP instrument out and it happens to catch a good earthquake that occurs in a place where we would really like to have had one, and the earthquake is big enough that we've got the seismic rays, then aces, we're in good. But still, this isn't going to fill in all the gaps.
Right.
Okay, did you know that there are over 1 million kilometers of ocean cables, transoceanic telecommunication cables in existence today lying on the seafloor? They come ashore in a terminal on one shore, they come ashore across the ocean somewhere else, and they send data all the way across the seafloor, but that's all they do. They're deaf, dumb, and blind, so they can't help us at all yet. But the internet would be not possible from an international perspective, from the World Wide Web perspective, if it weren't for these cables. And here you've got images of all the crucially important internet functions that we have, everything from Facebook and Google to banking to Zoom and WebEx and to kitty pictures.
We have to have Grumpy Cat.
We have to have Grumpy Cat,
And,
yes.
and look where they are. They are in many of those places that were just black, unknowable places.
Exactly.
from-
They cross, and
Yeah.
it's just like, oh, you can probably see where I'm going here. You get a cookie if
The
you can tell
cat-
where I'm going with
The cat
this.
is out of the bag. That'll be the third cat that we've mentioned so far now. Cat scan, Grumpy Cat, now this cat out of the bag.
There we
Okay.
go. Okay, well, we're on a roll. So, what is a transoceanic telecommunication cable? It is a big, fat cable. You can see the lady holding a cross-section in the middle that shows the one cable that crosses the ocean. And it goes from shore to shore. There's a cartoon in the upper left that shows you a cable laying on the ocean floor and then coming up as it comes towards shore. Usually they trench them in and bury them closer to the shore so they don't get caught by a trawler or a ship's anchor or get disturbed by a lot of the intertidal wave action or storm activity or something. But they're just laying on the ocean floor like you see down here. These days, the modern ones, which we will come back to, are fiber optic. That's how the data is transmitted. And about every 75 kilometers or so along these cables, which are thousands of kilometers long, they have a repeater. And what this repeater does is it helps to boost the signal to make sure that this very important internet signal gets across the ocean all those thousands of kilometers intact. And here's a picture of a great big ship that's used to deploy these ocean cables. So it's a major operation and it's very expensive, but obviously the telecom companies find it lucrative to do so because of all the internet commerce that's going on.
And they already have those repeaters on them.
They do
Isn't
have
that
repeaters,
cool?
yes. Another thing that is worth pointing out is that these cables have a limited lifetime. Their design life is maybe somewhere from 10 to 20 years. When a cable gets old, starts to wear out, or the technology has advanced enough that they would like to replace it with something with more bandwidth or that does a better job with the data, they go out and they spin out a new cable. And the new cable has repeaters. So, say hello to science monitoring and reliable telecommunications, or SMART cables. And the key to everything is these repeaters. The International Joint Task Force for the telecom cables, for the SMART cables, is working on designing new repeaters that actually contain seismic sensor, so that would be the accelerometers that are being pointed at here, also pressure and temperature sensors at the repeater and also several meters away from the repeater. And we're working with the telecoms to design a repeater that could be deployed while they're out there deploying the next cable that could actually have sensors on it and could transmit data back to the terminal on shore. Now, if we were to actually replace all of these cables, which eventually will happen as time marches on, and have sensors, smart packets, in all of the repeaters, we would have something like 20,000 additional seismic sensors that are crisscrossing the ocean floors that are currently blank right now as far as sensors go.
That cartoon that's at the bottom, Shar, is that pretty, except where it's indicated, dot, 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 10 to 15 meters, but is that fairly correct for scale? Because you showed us how fat that cable is
Yes.
just a little while ago, and now I see, how big around the actual smart package would be in there.
Yes, and it doesn't add much to the volume of the repeater as the current repeaters exist. We're trying to go towards miniaturized sensors. I am not an instrument person. I'm on the science committee for the JTF. I'm not on the engineering committee, so I'm not a good person to talk in detail about the actual hardware, but they've got several designs. This is the one that's sort of the mean of all the designs that have been come up with, and they're still discussing other options for how to sense the geophysical signatures, and we'll touch on that at the end of the talk. Okay? Well, what will the smart cables get us? They'll support climate, ocean circulation, sea level monitoring, global geophysical modeling, and also tsunami and earthquake monitoring and early warning, which would help society in terms of potential disaster risk reduction. They'll share the submarine telecom cables that are already there anyway or will be deployed in the future to replace the existing ones. And the Joint Task Force has actually got buy-in from UNESCO, so it's part of the United Nations supporting it, and we've got buy-in from a number of governments around the world, and some of the telecoms have bought into it, and they're very interested in this as well because it can also help them to sense disturbances that are happening that could impact their cables. So, back to geophysics for just a second. This is some work we did at Los Alamos. This is just to show you a little bit the improvement we can get just to seismic ray coverage in the Pacific for some hypothetical smart cables. In this little map here, kind of in the left center, the green lines are hypothetical smart cables that would replace existing telecom cables. And the two half donuts you see here are looking at the Earth's mantle and looking at seismic rays that go through the Earth's mantle from the distribution of earthquakes that happen to the distribution of on-land seismic sensors. And the one below it shows what you'd get if you added in the smart sensors. So you can actually image quite a bit more of the mantle. And we've got a depth cut here of the Pacific at a depth of around 1,300 kilometers, showing you again how much we could improve our ability to characterize what the rocks are like down there. And then below it, I've just got something in 3D for two hypothetical seismic events. One is located in Prince William Sound, Alaska, where the Great Alaska Earthquake occurred. The other one is located in North Korea. Don't know why we would have picked that one, but we're showing the seismic rays that will have been detected with existing stations on the left, and over here on the right, the ones that we would pick up if we had the smart sensors.
Right. You'd be able to pick up any kind of disturbance.
If it's big enough.
Yeah,
Yes.
if it's big enough.
If it's big enough. Okay, what else can society benefit from? Well, for one thing, over here we show a number of seismograms with increasing noise level on them. And that's a problem for seismologists looking for small earthquakes, because the farther you get from the earthquake, the more the seismic waves are damped out, and so the ambient noise is going to dominate to eventually you can't see the earthquake. So if we had smart cables crisscrossing the ocean here, we would be able to see earthquake sources that we know from some of those OPSIP deployments are occurring at these transform faults and spreading centers, but we just don't see them very often because there aren't instruments all along there. So we would be able to much better characterize the stresses that are occurring on the seafloor and the geodynamics that are going on there. And also, there's the issue of earthquake early warning. And this, mind you, is not earthquake prediction. Earthquake prediction, we're still a long ways from. What earthquake early warning is if you have sensors very close to an earthquake source, then you can send a warning at the speed of light over the internet or telecommunications in the air to critical infrastructure like gas pipelines, bullet trains, any place where several extra seconds to a few minutes of warning that the earthquake waves are on their way could help to save lives. Now, I've just shown you a couple of examples here, SNet and the two DONET. These are the Japanese government's subsea cabled arrays offshore of Japan, where they've got very dense instrumentation coverage, both seismic sensors and pressure sensors, so they get early warning for earthquakes and tsunamis. And it's been a very successful deployment. So if we are able to get the smart cables out where they're coming ashore at a variety of locations around the Earth that are earthquake prone, we can actually boost significantly the opportunities for earthquake and tsunami early warning. And what else? Well, we do have sea level sensors in terms of pressure sensors in these sensor packets, and we have thermal sensors or thermometers. And both of these are very critical for modeling climate change and sea level rise, as well as seeing tsunamis running across the ocean. So I've got here this car that's inundated. That's just high tide. That's not a hurricane or anything. But this is sea level rise, which is a result both of the glaciers melting and subsidence in some places of the Earth's crust near the shore, but also of ocean temperature increase, because as the ocean temperature increases, and we show in these models here where the temperature is going up, the water expands, so the sea level goes up. It also contributes to much more active storm seasons, and so as you know, we're getting a lot more hurricanes and named storms, all as a result of climate change. And to be able to better understand what's going on, we need a much more granular or fine resolution in our models of what's happening across the oceans.
Do we have much idea of the variation in temperature right down there at the ocean floor at this point?
The oceanographers do have some sensors out there. They're isolated sensors. They tend to be near shore, although there have been some deployments where they've gone and put something out in the deep ocean, but it's nowhere near the kind of high-resolution data that they could get if we got these smart sensors into the cable repeaters.
So we could be really increasing our understanding of what is happening at depth.
Yes, I think
with
so.
temperature. Fantastic.
And there are some wet demos or beta tests, pilot projects that are currently underway or in planning. The two that are the farthest along are the one here off of Catania, which is the big city on the island of Sicily. And then there's one in Portugal that they are currently in the process of deploying right now. So we're very excited about that, sort of a proof of concept for smart cables. There's also a plan for one from Vanuatu to New Caledonia, and then over here, one in French Polynesia. We're also planning some in the Western Mediterranean, one from India to Oman, Cayman Islands, New Zealand to the Chatham Islands, one in Angola. There's plans for one that would go from Perth to Darwin to Jakarta to Singapore to Malaysia. And the NSF is very interested in one that's being planned from New Zealand to Antarctica for Antarctic research to get data back. Right now, it's all satellite feed, and it's very band limited. Still better than what I had when I was working in Antarctica, but this would really boost the ability for scientists to do work and get real-time data back from the ice. And finally, I said I'd talk a little bit more about additional technologies. There's a technology, digital acoustic sensing, or DAS, which is all the rage in seismology right now, and it uses fiber optic cables. Fiber optic cables operate by transmitting data as impulses from lasers. And the cables are not perfect. There are irregularities and imperfections in the cables. So the laser, if you look at this little image in the bottom, it doesn't just all go right through. If it encounters one of these irregularities, it gets scattered, and some of it gets scattered back to the instrument that is sending out the laser pulse. Well, we can characterize very well exactly what the backscatter is for any cable, and we know what the signature looks like and how long it takes to come back. But if you have a cable that's deployed somewhere and you have an acoustic field or a seismic wave field that's impinging on that cable, it's disturbing it, it is straining it, changing the length just a little bit. That is going to change the return time for this scattered signal, and it's going to change what it looks like a little bit. So we can use the entire cable as a very finely divided network of seismometers. And what you see over here on the right is 600 channels off of a cable, and there are no additional sensors. This is the cable itself, just the backscattered laser, showing you signatures on all these channels from an earthquake that this example cable detected. So this is a really new, exciting technology. We're very interested in incorporating DAS into the smart cable systems, but it comes with its own problems. One of the biggest ones being that it's a fire hose of data. It's a huge volume of data, and so we would have to figure out how to deal with that volume of data, and that's going to require people who are really interested in developing techniques in artificial intelligence and machine learning to help us parse through this volume of data and get back the information that's actually important and useful.
That's fascinating.
Yeah, DAS is exciting. I got to do a DAS project last summer that was fun to do. So that's all I've got for the smart cables, and I just wanted to close it off by saying thank you for listening and show you a picture of yet another cat. This is Namatsu, who is the mythological catfish that the Japanese believe is responsible for earthquakes. When Namatsu moves, the ground shakes.
There you go. I love it. Wrapped all together. Fantastic. Shar, that was fascinating. And what interesting science behind it, what interesting technology is there, and what we can learn. Fantastic. Let me bring up some questions that have already come in. So remember, folks, we want you to write in some questions so that we can get this conversation going here. So I'm going to take us back to the OBSIPs that you mentioned earlier on, those individual instruments that they put down.
You want to go back to that slide? Or
No,
what you
let me
know?
just
Okay.
ask the question. What is the motivation of any group deploying them? So in other words, why were they deploying them? I mean, is it exploration, maybe searching for oil or geothermal or mineral extraction? Why do they do it?
There's a variety of motivations. I think most of the OBSIP deployments have been done to answer a geodynamic problem. For instance, deploying a bunch of them out at a triple junction where 3 plates are grinding against each other, and they want to be able to record all of the small local earthquakes and get a good picture of where the faults are so that they can characterize what's happening, how are the plates moving with respect to one another. Other OBSIP deployments are deployed at the spreading centers. Like, for instance, in the Pacific Rise, the spreading centers, they will actually go and put them out near the volcanoes where the lava is coming up and pushing the plates apart. And there are these wonderful features. They're called black smokers. You've probably heard about them, and they have all this really interesting deep-sea strange wildlife that lives in the vicinities of these black smokers. And so they want to better understand the geodynamics of what's going on there and the seismic signatures that are going on there. Some of them are deployed specifically for the purpose of active source exploration, not necessarily looking for minerals or oil, but wanting to do a good job of detailed imaging of the shallow crust and mantle. So they might put these instruments out and then come along with a ship with an air gun array, like the oil companies do, but they may not be looking for oil. They're looking for structure, looking for the geology, looking to see what's happening, say, if you get close to a subduction zone or something like that.
Yeah. Fascinating. So, let me just ask a question associated with it since you mentioned that. What is the average, is there an average, first I should ask, an average size of a quake that's associated with a spreading center? I've always felt that they were, even though it's active, it's seismically active, it's a quieter kind of event than what we see at
In Japan.
In Japan. Let's say in Japan,
Alaska.
anywhere around the
Yes.
Ring of Fire, right?
The size of an earthquake is directly related to the area of the fault that ruptures. So the width times the length gives you a pretty good estimate as to what the size of the earthquake may have been. Now, the ocean crust is very thin. The crust itself is at most about 10 kilometers thick compared to maybe 40 kilometers under the continents. Near the spreading centers, it's also quite warm. So once you get a little bit down into that crust, you're going to have rocks that are more likely to flow plastically than to break in a brittle fashion. So the earthquakes that you get are going to tend to be smaller. There is a size distribution. You'll have some that are bigger, some that are medium, and far more of them are going to be smaller. But you're not going to get your magnitude 7, 8,
No.
9 earthquakes there. They're
Yeah.
going to be smaller. So if you don't have sensors there, you probably won't see very many of them because the seismic waves spread out and they get attenuated. So by the time they get to the seashore,
Right.
it's going to be very difficult to see them with all the noise that we have on seismic data.
Right. So that kind of plays into this next question from our good friend Donovan Porterfield. How close do you need seismometers to be to reliably detect and measure an earthquake?
That depends on how big the earthquake is. There definitely is a distance relationship. I couldn't pull it out of my back pocket right now, but for the smallest earthquakes, for instance, when a volcano is preparing to erupt, I'll use that as an example because I know it very well. You get earthquakes that seismometers actually on the volcano can detect down to maybe a magnitude -1, -2. These are very small magnitude earthquakes. And your seismometer is maybe a kilometer or less away. As you get farther away, the earthquake has to be bigger because it's a noisy environment. And the seismic waves, as they spread out, any individual direction is going to lose a lot of energy with that spreading.
Yeah, makes sense. So now another question on this, another way to detect, it's not OPSIP, but DAS. Can DAS be used to identify the location of an earthquake? I guess it depends on where your cables are,
It depends
right?
on where your cables are. You're better off if you have a few cables, because you can think of the cable as being divided up into a whole bunch of little individual seismic sensors, maybe generally 1 meter or 10 meters apart, which on a multi-kilometer cable is a lot of data. So if the cable is optimally oriented so that you can leverage a technology called array technology, where you actually look at the delay of the P wave and the S wave as they, impinge on the cable, you might be able to use that to kind of back out where the earthquake came from. The distance to the earthquake isn't too hard because you just use the time difference between the P and the S arrival. It's like using lightning and thunder to see how far away a lightning strike was. But to actually get a good localization, you probably would need more than one cable, or you need the cable to be not linear. You'd need it in some configuration so it could emulate a seismic network or a tuned seismic array or antenna.
And then you'd triangulate or from all
Essentially,
of
yes,
that, basically.
Yes, you can
essentially.
figure the back azimuth if you have enough sensors in a configuration, say a circle, for instance. You can get a range of azimuths, and you can figure out the distance based on the waveform. And there's going to be certain error bars associated with it, but if you have more than one of those out, then you can knock your errors down quite a bit.
Yeah. Had they known for a long time, maybe even ever since fiber optic was invented, that you'd get this backscatter phenomenon with some, either disuniformity within the cable or something impinging on it, like the acoustic wave that you show?
I am not an optomechanical engineer, but I would guess that they've been well acquainted with the existence of these imperfections for a very long time.
Yeah.
By and large, they were just something that you get around, I think.
Right.
I don't know who first got the idea to use them and use strains on the cable. That I'm not as attuned to the history. I suspect it's been many years. There's lots of technologies that we use in seismology that maybe the satellite people came up with, or somebody in radio communications came up with, and some seismologists said, we could do that.
Right.
Yeah.
And as you mentioned, the real issue is the incredible amount of data that you'd get.
Oh, yes.
And needing to sort through it. So it's a problem of it's just so much we can't possibly. But with advances in computing and sensing and storing.
Yeah.
Yeah. and now, like you said, with AI and machine learning,
Yes.
to be able to parse that.
And we need smart, up-and-coming people and students who want to go into computer fields that would be a very applied work in order to address just these kinds of problems. The seismology is not the only science that's starting to have data overload and is starting to really look into machine learning and artificial intelligence to help us to do a better job at our jobs.
Yeah.
So if that's a field that interests somebody, I encourage them to look into it.
Yeah. It reminds me that the science of signatures is something that we talk about here at Los Alamos National Laboratory. If you don't observe it and record it, you can't do anything with it. It's as if it weren't there. So that opens up all of this array of technology and learning and recording and parsing for so many things to help us study so many new things that we never, ever thought that we'd have a chance to study.
And once you have all of that data, sometimes something just pops out of it that never even occurred to you. And you look at it, and it's like, well, of course. But so much science is, that's strange.
Right.
Yeah.
It's not, the big words aren't eureka, it's, that's funny.
Yeah.
Let's see here. How sensitive is the cable? How small are the earthquakes that can be detected? So I guess he's specifically talking about what would be on the smart cable, the smart
sensor itself. They could be talking about the DAS. I don't know. But the smart sensor, currently, the engineers who have designed the current iteration of what they're planning to use, and we're still having lots of discussions about this, they're planning on using accelerometers.
Yeah.
And accelerometers, again, I'm not a hardware person, but in my experience, they tend to be very sensitive to high-frequency shaking. I don't know how well they do with lower frequency shaking, which you might expect from distant seismic signals. As the seismic signals go through the Earth, they tend to get damped out, especially the high frequencies, whereas the long period or lower frequency things make it all the way through. And small earthquakes tend to be characterized by being much more rich in high frequencies. So just the physics of how the waves travel through the rock is going to limit the size, on the low end of what you can see depending on how far you are. I do not know the exact response curve for the accelerometers that they're talking about. I think they are fairly broadband and they should do a pretty good job, but I don't know for sure the answer to that. I think certainly any earthquake in the world, say magnitude 6 or above, no problem seeing it, I'm sure. Additionally, because these sensors are every so many kilometers along the cable, we can leverage some like delaying and stacking if we can figure out the direction waves might be coming from. And you can actually amplify your signal and knock down the noise by doing that. So these little array tricks might be able to make them more sensitive than if there were only one sensor.
A whole new industry.
Yeah.
Oh, so here's another question about the accelerometers. Are the accelerometers expected to be multi-axis?
Yes. In short, yes. So
yes.
You can get the ground motion in all three directions, which allows you to distinguish compressional waves from shear waves, and it would allow you to resolve surface waves, which kind of tend to have this elliptical pattern to them as they propagate along. So yes, three-component.
Just a question about the cables in general. When cables are laid across an expanse in the ocean, do they ever cross each other, or do they know exactly where they are and they very much try not to have them cross?
I think they try not to have them cross. I don't know if it's forbidden. I don't know what the potential hazards or risks to the cable might be for that. All of the pictures that I've seen, the maps, they tend to show them being pretty parallel where they're close together. I haven't noticed any that are crossing. So that would be a real puzzle to figure out how to get new cables in that aren't going to be impinging upon other cables. But I don't know if it's something that they actively try to avoid or not.
Any other sensors? Have they thought about any other sensors besides the accelerometer, but the pressure and the temperature sensors?
I believe they have. I think they're talking about hydrophones at least. And there may be other sensors that they are planning. I think the first generation of smart repeaters they're going to limit to pressure, seismic, and temperature. But there's certainly talks underway, especially with the climate people and the oceanographers, about what else on their wish list could they be able to work into these. I don't happen to know exactly what they are.
Yeah.
But I think I heard them say hydrophones.
Oh, that's interesting. Because maybe we didn't know what we'd learn if we'd only had listened.
Yes.
Right? Let's see here.
Can I ask a question?
Yeah, Mel, ask a
Okay.
question.
So imagine, so if I'm a telecommunications company and I'm laying down all this money to line the ocean floor with a cable, and a bunch of freeloading scientists coming to me and they're like, we want to put some sensors that generate so much data that we're going to be overwhelmed with data. What's in it for me? How in the world can you convince these telecommunication companies to load up their lines with all this stuff that's going to generate more traffic?
Okay. First of all, compared to the data that are being carried on these cables, ours is nothing. Okay? The smart repeaters, if we were to sample the seismic data at typical seismometer sample rate, that would be maybe 40 or 100 samples a second, which is absolutely nothing compared to real live data streaming that goes on all the time. It's so in the noise, the data volume itself is not a very hard sell. There have been discussions underway, and I guess I could move to this backup slide that I've got. Money and politics.
Ah, yes. Good. Your two hidden slides.
My two
here.
hidden slides, yes. So we're talking with the telecoms. Yes, there would be an incremental additional cost that would go into the repeater design. Compared to the millions and millions of dollars it costs to deploy a cable already, it's incremental. And of course, because they're in the business of making money, they still want to know what's in it for them. So trying to keep the cost low, pointing out that all of these sensors could help them quite a bit to detect and understand any hazards that their cables might experience. Being able to monitor what's going on in the vicinity of the cable, maybe state of health of the cable, these kinds of things. That's in their benefit, plus the PR of being able to say, oh, look, we're doing this and we're working with governments because earthquake hazard, tsunami hazard, these kinds of things. They themselves are very worried about sea level rise and climate change, and that works into their own bottom line. So some of the telecoms have already come on board and said, yes, absolutely, we would be very interested in doing this. Some of them still take a little bit of convincing, but we're working on getting additional support and buy-in from government agencies, foundations, international development banks, private companies, sovereign wealth funds, and we're working on the diplomatic and political issues, data access and ownership, sovereign coastal water control, how we're going to get the data out, the impact on ship tracking, military operations. They're talking to the Navy, making sure that they're not going to be seeing anything that they shouldn't be seeing. Economic activity, and there's discussions about liability and hazards and maintenance.
Great. Let's see if anybody else has something along that line. Ben said, I suppose you would have to kill me if you told me if any government intelligence agencies are adding their stuff like hydrophones to these cables. Just like you said, we shouldn't be listening to things that we shouldn't be listening to, right?
Right, and there certainly is going to be some influence from government agencies as to what might be permitted, for instance, in U.S. coastal waters.
Sure.
For observation, for bandwidth, for sampling rates, for things like that. There already are gobs of hydrophones under the ocean in various places all around.
Yeah.
And I suppose seafloor hydrophones would add an additional feature on there and might be able to see additional things. I am not privy to those discussions. I'm just a scientist, and I'm only on the science panel, so I'm only aware of these other things enough to be dangerous.
Could the sensors in the smart cables detect other events, such as ships wrecking on the seafloor, plane crashes, illegal nuclear tests, etc.? Rachel, this was from Rachel. She says, "Cool presentation, by the way. I found it very interesting."
thank you, Rachel.
You get some kudos there.
Thank you. These sensors could see other things. There's all sorts of anthropogenic noises that we could see, whether it's Chinese rockets crashing into the ocean and then hitting the seafloor, if there's big enough pieces of them. If a ship were to sink, I don't know how noisy a ship would be by the time it actually made it to the sea floor. My impression, and maybe it's just what I've seen from movies or something, is that by the time they get a certain distance down, they're moving fairly slow as they settle in. Although, if they settled in right near a cable, I suspect you would probably see something. As far as planes crashing or, let's say, nuclear explosions, if there were a nuclear explosion in the water, we would not need the submarine cables to see it, because the International Monitoring System has hydrophones all around the Earth, located at a depth of the water called the SOFAR channel. And that's the depth of the water where the sound speed is very slow, and it acts like a waveguide, and it traps the sound speed. And so the sounds are conducted very efficiently all around the globe, from anything that's happening like an explosion under the water. From nuclear monitoring perspective, we're more interested in keeping an eye on underground nuclear tests. And with those, that's what seismometers are used for, along with looking at earthquakes and looking at other things. So it's possible that these cables might be able to help us. That depends on how sensitive they are. One of the problems that we would have to deal with when these cables are deployed and when these sensors kind of land on the seafloor is looking at how well coupled to the seafloor they are. Because if it's not really well coupled, then it's not going to do a very good job of recording with integrity smaller signals. And so a really, really big signal, we might be able to see it, but we might not come up with a good estimate of just how big it is. So that is one of the technological challenges that we would face with these kinds of sensors.
Are there security restrictions on the cable locations?
Right now, the security restrictions are probably, well, they're ones that the cable companies themselves have worked out with the government for wherever the cable is coming on land. And I don't know if the question means, are the security people worried about where the cable is coming because it might be bad, or whether the question is the cable at risk when it comes ashore? And I could say that they've worked already to get the permitting for the government agencies to allow these cables to come up. As to whether the cable is at risk, anytime we deploy field gear, there is a certain security problem in terms of that can be at risk. We've had lots and lots of seismometers that have been ruined in the field because nearby villagers come and they steal all the solar panels, or they steal the batteries or the instruments. I've had bears tear them out of the ground. There's
Your Arctic hazards.
They get hit by lightning. There's all kinds of hazards to the equipment. And equipment security, and the flip side being security concerns about bringing a cable. That is between the government agencies and the telecoms.
Yeah. This is an interesting science one. Are there any efforts to use earthquakes and seismic sensors to create transfer functions, perhaps to characterize or map below the Earth's crust?
Not sure what they mean by the transfer functions. The earthquakes and sensors are of course, that's exactly what we use them for.
Yeah.
We map the subsurface. We can do that with earthquakes, with the sensors. You can do it in a more controlled way if you have a controlled man-made source, like a ship that's coming along with an air gun array, so you know exactly where and when you set that. So you've removed some of the uncertainties from the equation when you're trying
Right.
to characterize the subsurface. Lately, there was a big splash, I think it was in Nature, where someone who had a bunch of seafloor sensors was actually able to build a subsurface picture like the oil companies do using whale songs.
Oh, wow.
Yeah. Which I thought was like, of course, it's a seismic source and they
Right.
record them all the time. Why not use it? It's very high frequency compared to an earthquake, but you could characterize and map out the subsurface,
Wow.
a very shallow subsurface underneath the seafloor using whale songs.
Fascinating.
How cool is that?
Yeah, right, right. Again, a natural pulse.
Yes.
A natural emission. Very interesting. Let's see, we're almost out of time, right, Mel? Are we at about 6:35?
Yep.
Okay. Maybe there's one more question. One more question about DAS, which is such a fascinating technology. Using DAS, what kind of relative timing precision is needed to meet geolocation accuracy needs deep within the ocean?
Using DAS, although right now I don't know that they've been able to actually use DAS that far from the source and receiver. I think maybe about 100 kilometers is the outside that they've gotten so far. But the timing, of course, there's the timing of the laser pulse itself and its anticipated return. And that would be, I don't know, I guess that happens in terms of nanoseconds. Whereas seismic signatures, we tend to measure those at the most in milliseconds. That's close enough for government work, and the uncertainties of the rocks and the irregularities and the heterogeneities and everything. From our perspective for locating seismic sources, we tend to work down at the low end in the milliseconds, and certainly the speed of light and the backscatter from optical irregularities is going to be well within our error bars.
Right, right. Well, Charlotte, this was just fascinating.
It's been fun.
I thank you so very much for being with us tonight, and just opens our eyes about something else going on, new exploration, a chance to learn more, and the work of Los Alamos National Laboratory in doing this. So thank you so very much.
Thank you for having me. I've really enjoyed it.
My pleasure.
And great questions.
Our pleasure. And I want to acknowledge Mel Strong, our technical wizard over there. Thanks for your good question, Mel, and thank you for your support tonight. And thank you, everyone, for joining us tonight. We look forward to seeing you. Frontiers in Science coming up on the 26th. And there will be a Science on Tap in June. It will be some other scintillating scientists talking about their wonderful work. I just don't know who that is at this point in time, but I hope you're on our newsletter. But you can always log on to our website, www.lanel.gov/museum, and look under news and our events calendar to see what's coming up. Thank you all so very much. Until then, bye-bye.
Thank you.